Welcome to Part D for Unit 6 for our course on statistics. And in this unit, we have been looking at how to analyze data for studies where we have more than two groups and we are making more than two contrasts. We looked at how we can address an omnibus question, which involves the extent to which group membership explains variance overall in an outcome variable. And we have looked at how to address a focused question, which is where we make a contrast between just two things. And we saw how the omnibus question tells us whether there is some kind of general overall difference between groups, and the focused question can tell us exactly where that group difference is. In the previous section, we looked at how we can use orthogonal contrasts to address the focused question. Now, I want to make a distinction between two different ways we can address that focused question when we have more than two groups. So one way of addressing the focused question is to do something called planned comparisons, and the other approach is to do something called a post-hoc analyses. So with planned comparisons, that's what we were talking about in the previous section. With planned comparisons, I follow a set of rules, and these rules determine which specific contrasts I can or cannot make. And with a planned comparison, I'm not going to make every possible contrast that I possibly could make. So in the previous section, we talked about making orthogonal contrasts. And when we make orthogonal contrasts, we are doing planned comparisons. When we do orthogonal contrasts, we have to follow a set of rules that limit the type of contrast that we can make. For example, when we do orthogonal contrasts, the number of contrasts we can make is equal to the number of groups minus 1. So with orthogonal contrasts, we are only going to analyze a subset of all the possible contrasts that we could make, and we cannot analyze every possible contrast. So orthogonal contrasts are a type of planned comparisons. But now what if I want to address a research question that does not fit within the rules of doing an orthogonal contrast? What if I simply want to make all the possible comparisons between all the groups in my study? So in this case, I will use something called a post-hoc analysis. And a post-hoc analysis simply means that I'm not going to limit myself to the rules of doing a planned comparison, and instead I'm going to be free. I'm going to be free to make all the possible comparisons that I want to make. Now, the term post-hoc is a little bit misleading. It almost sounds as if it's describing a situation where a researcher conducted a study without a clear theoretical model or without a clear plan on how to analyze the data. And then the researcher decided after the fact, after the data were collected, what to do. But hopefully you always have a clear plan for data analysis before you start the study. Hopefully you always have hypotheses before you start your study. And the term post-hoc does not really mean that the researcher lacked a plan or lacked a hypothesis. Rather, it simply means that the researcher is free to make all the possible comparisons. So with planned comparisons, we're only going to analyze a subset of all the possible comparisons that we could make. And with a post-hoc analysis, we're going to be free to make all the possible comparisons that we want to make. So let's consider how we might proceed if we want to do a post-hoc analysis and do a study where we make all the possible comparisons between all the groups in a study. So say, for example, I was doing that study to investigate a treatment for statectomy sadness. That is, the sadness that students might experience after they complete a statistics course and they're grieving over the loss of being able to do statistics homework and have statistics tests, and they're sad because they no longer get to study statistics. And in my study, I had three groups. I had a control group, and the control group received no treatment. And then I had this noxious green gas aromatherapy that people experienced to see if that might help them with their symptoms of statectomy sadness. And then I have this enhanced treatment that gets both the noxious green gas aromatherapy plus coffee to see if that helps people recover from their statectomy sadness. So I have a sample of students with statectomy sadness, and they're randomly assigned to one of these three groups. Now, recall in this class, in a previous unit, we talked about doing simple contrasts. And a simple contrast was what we did when we wanted to make a comparison between just two groups. So we could just go back to the material we covered in that unit on simple contrasts and just make a whole bunch of simple contrasts here. We could make a simple contrast where we compare the control group with the regular noxious green gas aromatherapy. And we could do another simple contrast where we compare the control group with the enhanced therapy group. And then we could do a third simple contrast where we compare the regular treatment group with the enhanced treatment group. We could just do three simple contrasts to make all these comparisons. And on the right-hand side of the screen, I have some formulas and equations that were from that previous unit when we talked about doing simple contrasts. So for each contrast, we have I have this equation at the top of that cell, and that's the equation for variance in a sample. And recall that this equation has one key parameter estimate in it, which is the difference between the two means, y bar 1 minus y bar 0. And so in our unit, when we talked about doing simple contrasts, we talked about how we have this equation and we get that difference between the two means. And then we can convert that difference between two means into a d-statistic to get an effect size. And then we can test the significance of the difference between the two means with a t-test. Here I have the formula for the t-test. We take the difference between the two means divided by the standard error of difference between two means to get a t-value. And then once we have our t-value, we can determine the probability of that t-value if we have our degrees of freedom, and then calculate the probability of our t-value. So we could just do that. We could do a simple contrast where we compare the control group with the regular treatment, and then we could calculate our d-statistic for an effect size and do that t-test to see if there's a difference between the two groups. And then we'll do that again to compare the control group with the enhanced treatment group, and then do that a third time to compare the regular treatment with the enhanced treatment. And we'll simply make all the possible comparisons. In each case, we'll calculate a d-statistic for an effect size, and then we'll use a t-test to test the significance of that contrast. And essentially we could do that, but there's going to be a few issues we need to address along the way. Because we have more than two groups, that's going to raise a few issues. So we'll need to see what are these issues we will need to address if we're making more than two contrasts. So if I have more than two groups, and I simply want to make a whole bunch of simple contrasts, one of the issues I need to address is that I'll need to make a few adjustments in the process I use to do my t-test. And one of those adjustments pertains to the degrees of freedom that I use. So recall in our previous unit when I talked about doing a simple contrast, I said our degrees of freedom was equal to n minus 2. But that's no longer going to be the case if I have more than two groups. Because if I have more than two groups, I'll need to take into account all the groups that were included in the study. Even though I'm making a comparison between just two groups, my degrees of freedom will need to take into account all the groups that I had in my study. And specifically, my degrees of freedom are going to be equal to the error degrees of freedom from my ANOVA table. That within group degrees of freedom from our ANOVA table, which is equal to n minus p minus 1. And if you recall, p is equal to number of groups minus 1. Or, as we saw in the previous unit when we were doing orthogonal contrasts, p is equal to the number of predictors you would use if you're doing the orthogonal contrast approach. So we no longer use n minus 2 as our degrees of freedom, and instead we use the error degrees of freedom from the ANOVA table, which is equal to n minus p minus 1. So that's one change we need to make. And then there's one other change we need to make when we do our t-test, and that pertains to how we calculate the standard error of our statistic. So recall that to calculate our t-value, we take the difference between the two means, that mean difference, divided by the standard error of our statistic, that is the standard error of mean difference. And recall that to calculate a standard error of mean difference, we need to calculate a pooled variance. And also recall, I talked about previously in a previous section, the fact that the mean squared error from our ANOVA table actually gives us a within group pooled variance across all the groups in our study. So instead of using a pooled variance for just two groups, we're going to use a pooled variance, which is this mean squared error, because that's the pooled variance across all the groups, and presumably that will give us a more accurate estimate of the pooled variance than if we just used two groups. So let's see exactly how we would do that. So this screen shows you two formulas for calculating a standard error of mean difference. The top formula is the formula that I showed you in the previous unit when we were talking about doing a simple contrast between just two groups. And we talked about how we would calculate the pooled variance for those two groups. And then to calculate our standard error of mean difference, we took that pooled variance and divided it by the sample size for group 1. And then took that same value, that same pooled variance, and divided it by the sample size for group 2. And then added those two things together and took the square root, and we had our standard error of mean difference. So that's the formula that I gave you before, based on a situation where we have just two groups. But now if we have more than two groups, we're going to assume that we can get a better estimate of what that pooled variance is if we pool across all the groups in our study, not just the two groups we're comparing. And recall again that mean squared error from our ANOVA table gives us just that. The mean squared error gives us a pooled variance across all the groups in the study. So that's what we're going to do. So we'll take that mean squared error and we'll plug it in there and divide our mean squared error by the sample size of group 1. And then we'll take the mean squared error, that's the exact same value, that mean squared error, and divide it by the sample size for group 2. And then we'll add those two things together and then take the square root, and that will give us the standard error of mean difference for a situation where I have more than two groups in my study. Now, there is another issue we need to address if we have more than two groups and we simply want to make a whole bunch of simple contrasts. This issue is something called family-wise error. This is something we could have talked about much earlier in this class. It is an issue that has been lurking beneath the surface in all the different analyses we've been discussing up to this point. But it is an issue that becomes especially important when doing post hoc analyses. So, when we do significance testing, we call results significant when the probability is less than 0.05. This means that if the null hypothesis is true, we will make the correct decision 95% of the time, and we will mistakenly call results significant only 5% of the time if the null hypothesis is true. In other words, we set the type 1 error rate at 5%. Recall that the type 1 error rate only applies to situations when the null hypothesis is true, and it is the probability of incorrectly calling results significant when the null hypothesis is true. So, when we use the rule that we only call results significant when the probability is less than 0.05, we are setting the type 1 error rate at 5%. When the null hypothesis is true, we will make the wrong decision and incorrectly call results significant only 5% of the time. That is, we will mistakenly call results significant only one time out of 20. Now, consider this. what happens if I do more than one significance test, and the null hypothesis is true for everything I am testing? For example, what if I do 5 significance tests and test 5 different effects? If the null hypothesis is true for every test, what is the probability that I will mistakenly call one of those tests significant? The more significance tests I do, the more chances there are for me to make a type 1 error, and the more chances there are for me to mistakenly call results significant when the null hypothesis is true. And so the family-wise error rate is the probability of incorrectly calling one effect significant when we do several significance tests and the null hypothesis is true in every case. It is the probability of making a type 1 error for a set of statistical analyses or for a family of statistical analyses. That's why it's called the family-wise error rate. Now, notably, this issue is relevant anytime you do more than one significance test. And just about any research study anyone ever does will probably use more than one significance test. I can't imagine doing a research study where I only do one single significance test. So this is an issue that would be relevant in just about any research study. It would be relevant if you test the significance of more than one correlation, or if you test the significance of more than one beta weight, or if you test the significance of more than one contrast. However, there are some situations where researchers have tended to ignore issues of family-wise error, and other situations where they have tended to be especially concerned about it. And one place where they tend to be especially concerned about it is when doing post-hoc analyses. I think part of the reason for this is simply tradition. For whatever reason, this happens to be one area where researchers have traditionally been concerned about family-wise error. However, another part of the reason for this is that if you have a large number of groups and we're testing every possible comparison, well, that could result in quite a few significance tests. And here is an example that will illustrate the problem of family-wise error. So this example is from a study that I did where I got a sample of 43 people, and some of the people in the study were men and some people were women. And I asked each person how much they liked 20 different random things, and to rate on a scale of 1 to 10 how much they liked each object. So how much do you like socks? On a scale of 1 to 10, how much do you like socks? On a scale of 1 to 10, how much do you like cups? And so then I asked about how much they like seatbelts and thermostats and gophers and wombats and goats and several other random objects. And then for each of these objects, I did a simple contrast. I tested for a gender difference. I wanted to see if there was a difference between men and women and how much they liked each object. So for socks, I did a simple contrast, and I calculated a D statistic to give an effect size for the difference between men and women. That D statistic was 0.07, so a very, very small effect. And then I calculated a T value, and then I determined the probability of that T value and used that for a significance test. And in the second column, I have the probability values from all my T tests that I did, all my significance tests. And we see that my probability value for socks was 0.83. That's not less than 0.05, so that's not significant. And the probability for cups was 0.2, so that's not significant. For seatbelts, I got 0.08. That's getting a little close to 0.05, but it doesn't cross that threshold, so it's not significant. And you'll see everything, all my results in this first column, these are all non-significant. I did not find any significant gender differences for any of those objects. However, look in the second column over here for chalk. Look at this. I got a significant gender difference for chalk. I found that women like chalk more than men. I got a D statistic of 0.75. That's a medium effect and getting kind of close to a large effect. And my p-value, the p-value I got for my t-test was 0.03. That's less than 0.05, so that's significant. So I got a significant gender difference for chalk. So now consider this. Why would it be inappropriate for me to make a claim to have discovered something? Why would it not be good for me to make a claim that I've discovered a gender difference and that women like chalk more than men? Well, the answer is we need to consider family-wise error rate, because if the null hypothesis is true, and I do 20 significance tests, I would expect 1 out of every 20 significance tests to be significant. If the null hypothesis is true, I would expect that I will incorrectly call results significant if the null hypothesis is true 5% of the time. That is 1 out of every 20 times. And that's exactly what happens here. I did 20 different significance tests, and out of those 20 tests, 1 was significant, and that's actually exactly what I would expect if the null hypothesis is true. So if I look at this one finding, the finding I got for chalk just by itself, I say, wow, I got a significant finding there. That's exciting, it's significant. But then if I take a step back and look at it in the context of the fact that I did 20 different significance tests, I need to take that into account and realize, oh, I really shouldn't call that significant. I really shouldn't claim to have discovered something, because this is actually exactly what I would expect if the null hypothesis is true. I would expect to get 1 out of 20 of my results to be significant if the null hypothesis is true. And that's the issue of family-wise error. So if we're going to address the issue of family-wise error when doing multiple contrasts, we will need to keep track of how many contrasts we are testing. If we do a study and make all the possible comparisons between individual groups, how many comparisons is that? So one way to answer that question is simply to think of all the possible contrasts and then count how many there are. For example, say I have 3 groups. I could have group 1, group 2, and group 3. And so if I have 3 groups, I could compare group 1 with group 2, and I can compare group 1 with group 3, and I can compare group 2 with group 3, and altogether I've got 3 different comparisons I can make. I can make 3 different group contrasts. Or over here on the screen, I have a situation where I have 5 groups, and if we count up all the possible contrasts we can make between 5 groups, you will see we can make 10 possible contrasts. So you could just think of all the possible contrasts and count them up. Or another way to determine this is to use this formula that I have at the top of the screen. And this will tell you the number of possible comparisons you can make given the number of groups you have. So in this formula, K is the number of groups. So if you take K times K minus 1 and then divide that by 2, that will tell you how many possible comparisons you can make in a study given the number of groups you have. So for example, if we have 5 groups as we have over here, we take 5 times 5 minus 1 and then divide that by 2 and we get 10. So we could count up all the lines we have over here and we see we have 10 lines, or we could plug in the formula and see we can make 10 possible comparisons between groups if we have 5 groups. So exactly how can we address this issue of family-wise error when doing multiple contrasts? It turns out that there are many different options, and there have been lots of papers published and arguments made about which option is best. So I'm going to tell you about just 3 of these options, and specifically I'm going to talk about what seem to be the 3 most popular options. Now, with each option, the goal will be to protect ourselves against family-wise type 1 error. If the null hypothesis is true, and that's an important piece, if the null hypothesis is true for all of our analyses, we want to hold the probability of error at 5%. That is, we want to hold the probability of incorrectly claiming something is significant at 5%. And we want to keep this probability of error, if the null hypothesis is true, we want to keep that probability of error at 5% for the entire set of analyses we are doing. So, in describing these options, it's going to sound a little bit like the story of Goldilocks and the Three Bears. One option will be a little bit too lenient, and it will not sufficiently protect us if we want to hold the family-wise error rate at 5%. And another option will be a little bit too strict, and it will overprotect. And then a third option will be just right. So let's look at these options. The first option I have here is something called Fisher's Least Significance Difference Procedure. And it can be abbreviated Fisher's LSD, not to be confused with the drug LSD, but it's Fisher's Least Significant Difference Procedure. And this is a fairly simple thing to do. All we do is this. First, we do that omnibus test and do an F test to see if we have a significant omnibus effect. And recall that that omnibus test is testing to see if group membership explains a significant amount of variance in the outcome variable. It's testing to see if somewhere you have some difference between groups. If it's significant, it means you have some group difference, but it doesn't clarify where that group difference is. So with the Fisher's LSD approach, we first do that F test. We first do that omnibus F test to see if we have some kind of significant difference between groups. And if that F value is significant, we use that as a license to say, okay, now it's okay to go ahead and do all the contrasts and do all the comparisons we want to do. So we can proceed to do a whole bunch of simple contrasts and test them with t-tests for all the comparisons we want to make. So the basic idea is that we first do that omnibus F test. If it's significant, that gives us a license to do all the simple comparisons we want to do and to do a whole bunch of t-tests that we want to make for each one of those simple comparisons. And if our F value is not significant, then we don't have the license to proceed and we don't do any further testing. We don't look at any of those simple effects if our overall F value is not significant. Now, this approach will help protect us against family-wise error rate, but if we want to hold our family-wise error rate at 5%, it won't quite sufficiently do that. So it won't sufficiently protect us against family-wise error, although it certainly helps somewhat. So this is one option we could use, although one disadvantage of this option is that it doesn't sufficiently protect us against family-wise error. Another technique we could use to protect ourselves against family-wise error is to do something called a Bonferroni correction. And a Bonferroni correction is a very easy thing to do. We just get a p-value for a statistic, and then we multiply that p-value by the total number of significance tests that we have performed. And that will give us a Bonferroni corrected p-value, and then we use that corrected p-value to make decisions about significance. If that corrected p-value is smaller than 0.05, we call the result significant, and if it's not smaller than 0.05, we don't call it significant. So for example, what if I was doing a study where I had more than 2 groups and I was making multiple contrasts? Say for example, I had 4 different groups. So if I have 4 groups, how many different contrasts can I make? I could compare group 1 and 2, 1 and 3, 1 and 4, 2 and 3, 2 and 4, 3 and 4. All together, I could make 6 different contrasts if I have 4 groups. So if I was using this Bonferroni procedure, I would go through and I would make each of my 6 contrasts, and for each contrast, I would calculate a t-value. I'd calculate my t-value for each contrast, and then once I have my t-value, I'd calculate the probability of that t-value using the usual way. So I'd get a p-value, and then I'd multiply each of those p-values times 6. Because I'm doing 6 total contrasts, that means I'm making 6 different significance tests. So I multiply each p-value times 6. I multiply each p-value times the number of contrasts that I'm doing, and that gives me a Bonferroni corrected p-value, and I would use that to make decisions about significance. Or for example, we looked at that study I did where I found a gender difference between men and women and how much they liked chalk. And in that case, I had a p-value of 0.03. But recall in that example, I had done 20 different t-tests. There were 20 different significance tests that I'd done, and just one of those was significant. So if I were to do a Bonferroni correction for that study, I'd take this p-value of 0.03 and multiply it by the number of significance tests that I did. And I have that down here. The corrected p-value is 0.03 times 20. I get a corrected p-value of 0.6. That is definitely not less than 0.05. So if I do this Bonferroni correction, I would say this effect was not significant. Now, this Bonferroni correction procedure has a couple key advantages to it. One advantage is that it's simply very easy to use. You simply get the p-value for a statistic, and then you multiply that p-value by the total number of significance tests that you've performed, and there you go. You have your Bonferroni corrected p-value, and that's all there is to it. Another big advantage is that the Bonferroni correction, this procedure ensures that your family-wise error rate is not inflated. Recall when I talked about that Fisher least significant difference procedure, that procedure didn't fully protect us against family-wise error. But with a Bonferroni correction, that will definitely fully protect us. If you use a Bonferroni correction, then you could be certain, you could be confident that your family-wise error rate will not exceed 5%. However, the one disadvantage of this Bonferroni procedure is that it often overcorrects. It corrects more than it needs to. It will ensure that your family-wise error rate doesn't exceed 5%, but oftentimes it will ensure that it's an even smaller value. So that means that there may be some times where you do a study and get a result, and if you use the Bonferroni correction, it might identify that result as non-significant, when in truth you could justifiably call it significant. And that would be kind of a sad thing if you put a whole lot of work into a research study trying to discover something, and you get a non-significant result saying you failed to discover anything. That could be kind of disappointing, and it would be unfortunate if you labeled a result as non-significant when you didn't need to. So one big disadvantage of the Bonferroni correction is that it often overcorrects, and it can lead you to calling things non-significant when you don't really need to call them non-significant. And a third option that we can use to protect ourselves against family-wise error is to do something called a Tukey's honestly significant difference test. And this is sometimes simply called a Tukey test. And the Tukey test is based on a statistic called the studentized range statistic, and that's indicated with the letter Q. Now, this is a lot of words to describe something that's actually very simple, because Q is simply a linear function of a t-test, and Tukey has simply provided tables that we can use to determine if our Q is significant after correcting for family-wise error. So that's essentially all there is to it. So to calculate this Q statistic, Q is simply a linear function of t, and we take our t value. So if we do a study and we calculate a t value, and we get that t value and we multiply it by the square root of 2, and that gives us Q. And I'm not sure how much mathematical benefit there is to having a separate statistic called Q if it's simply a t value multiplied by the square root of 2. However, it does provide the benefit in that it makes it easy to clarify which statistics we're talking about. If we're doing a Tukey test, we'll be using a statistic called Q, and because we call the statistic Q, it's not likely to be confused with the ordinary t-test. And so the key thing to know about a Tukey test is that Tukey provided tables providing critical values of Q based on the number of groups being compared. So instead of using t-tables to make decisions about significance, we can use Tukey's tables for critical values of Q to make decisions about significance, and this will protect us against family-wise error rate. And a Tukey test has a couple key advantages to it. One advantage is that, like the Bonferroni, it will ensure that your family-wise error rate is not inflated. Both with the Bonferroni and with the Tukey test, if you use these procedures, you can be confident that your family-wise error rate will not exceed 5%. And unlike the Bonferroni, the Tukey test is less likely to overcorrect. A Tukey test might overcorrect just a little bit, but not that much, and not as much as a Bonferroni. So if you're using a Tukey test, you're much less likely to have that sad situation where you call results non-significant and say you failed to detect anything, when really you would have been justified to call your results significant. So that's a big advantage for the Tukey test. One disadvantage is that it's not really convenient for hand calculation. To calculate a Tukey test, you would either need to have access to Tukey's tables, or more commonly what we do is we use computer software programs to calculate significance values for us based on Tukey's tables. And if we don't have access to that software, it's hard to calculate by hand. So if you're doing something by hand, a Bonferroni can be a very handy thing to do. But for most of our analyses, and in this class, whenever we're doing post-hoc analyses and we want to do all the possible comparisons and control and correct for family-wise error rate, the Tukey test will probably be the best way to go. So we'll use the Tukey test as the default procedure to protect against family-wise error rate when we're doing post-hoc analyses and making multiple contrasts. So this has been a unit on multiple contrasts. We have been looking at how to analyze data when we want to make comparisons between more than two groups. And this slide provides a summary of the key statistics to use when doing this type of analysis. And we have seen how there's two basic types of questions to address: an omnibus question and focus questions. And the omnibus question has to do with the extent to which, in general, there is a difference between groups. Specifically, it has to do with the amount of variance in an outcome variable that has been explained by group membership. So, what are the statistics that you would use to address the omnibus question? So, if we're addressing the omnibus question, the descriptive statistic that we will use to give us an effect size, our effect size will be eta squared. And eta squared indicates the percent of variance explained. And then the inferential statistic that we will use to test the significance of our effect size, our inferential statistic will be the F statistic. So if we're addressing the omnibus question, our effect size is eta squared, and our inferential statistic is the F statistic. So the other type of question to address, the other questions are the focused questions. And we can address the focused questions by testing contrasts to clarify exactly where group differences exist. And as we've seen, there are two options for how to address the focused questions: planned comparisons and post-hoc analyses. So planned comparisons and post-hoc analyses are the two approaches we can use for addressing the focused questions. Now, if you're addressing a set of hypotheses that can be addressed with planned comparisons, then that is the best approach to take. But if you're addressing hypotheses that do not fit the rules for planned comparisons, or if you simply need to make all the possible group comparisons, then you need to use post-hoc analyses. Note that you have to choose one option or the other. It's not possible to do both, because the moment you do post-hoc analyses, you are no longer doing planned comparisons. Part of doing planned comparisons is that you only consider a subset of contrasts that are allowed by the rules for the planned comparison. And the moment you consider results from a post-hoc analysis, you are considering additional contrasts that were not allowed by the rules. And the moment you violate the rules, you're no longer doing planned comparisons. Now, on homework and assignments, I might give you examples that include statistical output for both planned comparisons and post-hoc analyses. But if we're working with an example that involves a planned comparison, you should completely ignore any statistical output for a post-hoc analysis. And if we're working with an example that involves a post hoc analysis, you should completely ignore any statistical output for a planned comparison. So, if we're doing a planned comparison, what are the statistics that you should use to address your planned comparisons? Now, the planned comparison approach that I showed you here, I've showed you how to make orthogonal contrasts. There are actually other types of planned comparisons you could do, but orthogonal contrasts are probably the most important type. So if we're doing planned comparisons, we're going to make orthogonal contrasts, and then what statistics will we use to analyze our orthogonal contrasts? So the descriptive statistic that we will use to give us an effect size if we're doing orthogonal contrasts will be the D statistic. So the D statistic will be our effect size, and then the inferential statistic that we will use to test the significance of that effect size will be the t-test, and we're actually going to do a t-test on a beta weight if we're doing orthogonal contrasts, and that t-test will test the significance of our effect size of that D statistic. Then, what about post hoc analyses? What if we're doing post hoc analyses? What statistics will we use to analyze our data if we're doing post hoc analyses to address that focused question? So if we're doing post hoc analyses, we're going to make all the possible contrasts between different groups, and our descriptive statistic to give us an effect size will once again be the D statistic. So the D statistic will be our effect size for both planned comparisons and post hoc analyses. But what is the statistic that we will use? What is the inferential statistic we will use to test the significance of that effect size if we're doing post hoc analyses? If we're doing post hoc analyses, our inferential statistic will be that Q statistic, and we will use that with doing a Tukey test. So if we're doing post hoc analyses, our inferential statistic will be Q, and we'll be doing a Tukey test for our inferential statistic to determine the significance of our contrasts in a post hoc analysis. So that is a summary of the statistics to use when making multiple contrasts. And this completes everything for Part D of Unit 6.